Power decibels AC, and it's just a little few pages here, I'll tell you. But it stumped me right away. Recall Ohm's law from your tech training. Yeah, they're relying a lot on your tech training here. So um, E equals IR, which E being voltage, I current, and R resistance. And and yeah, I was telling Wes, I got a little handout. Um, I don't know how many are you guys familiar with algebra and real comfy with it? Because when they start doing this stuff, you're familiar with this, how you can move the R from one side of the equation to the other and all that. Sometimes I teach this class and guys just zip right through it and you don't have to explain much, but that's what they're doing here. It's just basic um, algebra and oops. And then there's power. And we did this in, or you did this in the tech class, I believe. Power equals voltage times current. And then you can do the algebra to get either voltage or current if you know the other two. Um, basically, you like if you take the original equation of you probably guys probably can't see my arrow, can you? Let me see if I can make an arrow here. No, that ain't gonna happen. Never mind. Oh, shoot. Oh,
I could see an arrow, John.
can you? Yeah,
Yeah.
so you take the first one and you divide both sides by I and you get E equals P over I. And then the second one, you divide both sides. You take the first equation, divide both sides by E, and you get I equals P over E. I don't know how comfortable you guys are with that math there. Because there'll be more of it. And Wes is doing next week, I believe. There's some more of that going on there. Continued. Substituting Ohm's law equivalents for voltage and current allows power calculation using resistance. These are just pretty common equations you use trying to evaluate circuits. So you can figure the power. This is, I don't know why this one's so famous. I squared R. It's just, it's really I squared R losses, we call them, because it's power that you lose. Um, and you can also figure power by squaring the voltage divided by resistance. To find out how many watts of electrical power are used in okay, this is right out of your question, so you're going to pay attention. An electrical power used at 400 volts DC is supplied to, I can't read it, a 800 ohm resistor. Okay, let me move my screen around here. So how do you do that? E squared over R, because you have the voltage, you have the resistance. So in theory, you should be able to figure power. So it's 400 squared over 800, which is 200 watts. And then there's more. To find how many watts of electrical power are used by a 12-volt DC light that draws 0.2 amps. So you go, well, 0.2 times 12, basically, which is 2.4 watts. To find out how many watts are being dissipated when a current of 7 milliamps flows through a 1.25 kilo ohm resistor, ta-da! You, yeah, you get rid of the millis and the kilos, so you do 0.007, which is 7 milliamps, and you use 1250 instead of 1.25 K. So it's 1250 times 0.007 squared, ta-da, 0.061, which is 61.25 milliwatts. And you know, these questions on your test will be A, B, C, D kind of thing. So um, don't have to worry about 0.25 too much. Calculating power or voltage ratio from dB. Now this one sent me back to the manual. Oh, this, of course, he didn't get his little divider here very well. I didn't get it cleaned up. But I think we've been through this before, right? It's dB over 10, or the power ratio. Um, the power ratio is equal to the anti-log of dB over 10, voltage ratio, um, the inverse log of dB over 20. I don't know why they present it that way, but that's what they wanted to do. Inverse log notes referred to as either a log to the base 10 minus 1, log to the minus 1. Yeah, some texts use the capital log um, instead of the, sorry, let me try to get these screens straightened out here a little bit. On scientific, oh, we did that, huh? Scientific A log is either inverse log, A log, 10 to the X, which I just missed on the Windows calculator. Inverse, inverse then log. Huh? Well, it's the anti-log. Oh, they're saying you can hit the inverse key and then the log key to get the inverse log. That's what they're trying to do there. Okay. So now the power ratio. I'm really going to try to get this picture of all you guys out of my face. No offense, but it's messing up my screen. Okay, power ratio of 9 dB is the inverse log of 9 over 10, which is 0.9. The inverse log of 0.9 is 8. So a 9 dB power ratio is 8 times. That's what they're trying to say here. A voltage ratio of 32 dB is the inverse, because it's, as you remember, the original equations, the power ratio is 10 log ratio and the voltage is 20. So that's the difference between the 10 and the 20 here. Voltage is 20. So anyways, 32 divided by 20 is 1.6. The anti-log of 1.6 is 40. Let's see what else they got to surprise us with. If you double power or cut it in half, that's 3 dB change. We had that last time, I believe. So here you go. You take, if you double the power, that's 2. So 2 over 1, 10 times the log of 2 is 10 times 0.3 is the log of 2. So it's a 3 dB if you cut it in half or double it. Either way, it'd be a minus 3 dB, of course, if you cut it in half. Now the percentage one, this is on your test. And, you know, I don't know anybody that really does this calculation, but boy, you got to do it. So converting dB to percentage or vice versa. Um, of course, the percentage of power, so if you were talking 20%, it would be 20 over 100, or in this case, and then the difference here is whether you're using voltage or power. Power, it's 10 times the log. Voltage, it's 20 times the log. And bleh. So what are they trying to tell us here? Percentage power is 100% times the inverse log of dB over 10, or percentage voltage, which I don't know who would want that, is inverse log of dB over 20. But this first one, percentage power 100% times inverse log of dB over 10, that one will be on your test in some form or another. Suppose you are using an antenna feed line that has a loss of 1 dB. You can calculate the amount of transmitted power that's actually reaching your antenna and how much is lost in the feed line. Okay, you use the percentage power. calculation. So 100% times the inverse log of -1, because it's a 1% loss. Well, wait a minute. Did I say that right? Suppose you're using it as a loss of 1. Yeah, so that's the 1 dB -1 because it's a loss. And since it's power, you divide by 10. So 0.1 inverse log is, by the time you multiply it by 100, you get 79%. But that is the power going through, not the loss. See, it says percentage power. It don't say percentage power loss. I find it very confusing because it's a 1 dB loss. Yeah, when I was working through these just before you guys showed up, I was really stumped. I just remembered it was a hard one. So 79% of your transmitted power reaches the antenna, 20.6% is lost in the feed line, which is the question on the test. Okay, move all the icons around again. And current is the flow of electrons measured in amps with an ammeter. Voltage is the force that moves the electrons measured in volts with a voltmeter. Polarity of voltage refers to the direction from positive to negative. Power is the product of current times voltage measured in watts. Boy, that I just don't. It seems like I got things out of order here. Didn't we just do this? Ohm's law states that R equals E over I equals E over R, and the master equation E equals I times R. The voltage caused by a current flow through a resistance is called the voltage drop. And E equals IR. So this is a way to remember these equations over here. So the top one, E, if you want E, you divide it by I. No, yeah, you divide it by I times R. If you want I, you divide E by R. If you want R, you divide E by I. That's how you're supposed to read this circle thing. And it's just a tool to help you remember that. Oh, Larry's here. So that's what this little circle's about. So R equals E over I equals E over R, and E equals IR. So that's what that's about. Okay, frequency review. We're just going to move right along. A complete sequence of AC current, alternating current, flowing, stopping, reversing, stopping again, is a cycle. Yeah, I think we knew that. The number of cycles per second is the current's frequency measured in hertz. Good old hertz. A harmonic is a frequency at some integer multiple of the lowest fundamental frequency. Boy, this seems like we covered this, didn't we? The harmonic is twice the frequency. No, the harmonic at twice the frequency is the second harmonic. 3 times is the third harmonic. There is no first harmonic. Okay, wavelength review. The speed of light is 300 million meters per second, somewhat slower in wires and cables, yes. Wavelength is the ratio. What wavelength of radio wave is the distance it travels during one complete cycle. And lambda is what they're using for wavelength. So it's the speed of light, which is c, divided by the frequency. The frequency is the speed of light divided by the wavelength. Either way, you can flip it back and forth, talk about them the same way. The radio wave can be referred to by frequency or wavelength because the speed of light is constant, more or less. Series and parallel circuits. Well, this one, well, I think a lot of this is next week, but we're going to start here. Any complete path through which the current can flow, that is a circuit. a complete path through which current can flow. Series circuit is two or more components are connected so that the same current flows through all the components. The old, this is a lot easier when we had the series Christmas tree lights to explain. Parallel circuit, two or more components are connected so that the same voltage is applied to all the components. So I hope that's obvious. Then we go to dB.
And you might also mention in the current divides.
The what?
And the current divides.
Current divides.
Yeah,
Oh,
in a parallel circuit, current
yeah,
divides doesn't all go through one resistor.
yeah. And so the voltage is constant across all the components. Same way here in the series, the current flow is the same through all the components, but there's a different voltage, or can be a different voltage across each one. I don't know. I find it easier to understand with the circuit myself. But moving right along, we have the dB, the good old dB. And I don't know, did you guys cover this in your tech class? I don't remember. It's basically 10 times the base 10 log of the power ratio, or 20 times the base log of the voltage ratio. There it is. And what else do we have here? Comparing a measured power or voltage to a reference value. Oh yeah, that's the thing about dB, is it's a ratio. It's not any one unit like watts or I mean, sometimes they'll say a dBm, which means dB's reference to milliwatts. So here's the basic equation: your reference power to the measured power to the reference power. This would give you hopefully a positive number, and then 20 is the voltage ratio measured to reference. Positive values means the ratio is greater than 1, meaning a gain. Negative values are called loss or attenuation. It's a loss, it's attenuation if you want it. It's a loss if you don't. That's my guess. Well, let's see how much I can mess this up. Practice questions. Okay. What dB change represents a factor of 2 increase or decrease in power? Now this, I believe, is a rerun question. I think we had it last week too, in a different form. Well, I almost said the answer. So if it's a ratio of 2, either increase or decrease, that would be a plus or minus how many dB? And that's any guesses there? 2, 3, 6, or 9?
Yeah, 3 dB.
Thank you. Yeah, we had that last week, I think. 3 dB. That's one to remember. And then next is how many watts of electrical power, oh, this is, get your calculators out, are used if 400 volts DC is supplied to an 800 ohm load. So we want to calculate power based on voltage and ohms, voltage and load. So the equation, as you may remember, is V squared over R. So this is where calculators come in handy. I mean, some people can do it in their head. And some people I see do this test by just getting a ballpark number and then figuring out which one of those 4 answers are closest, you know. And that can fool you sometimes, but because here you go taking 400 and squaring it, which would be 16 with 4 zeros behind it. And then you divide it by 800. So 16 divided by 8 is
400 watts.
How many?
I think that's what it is.
I think it's 200. Yes, 200.
Did I screw up? I guess I did.
Yeah, because 400 squared is 16, 160,000, I guess, and divide that by 800 is 8 into 16 is 2. And then straighten out your zeros, you know.
Oh, I used 800 volts. Sorry about that. Yeah, I did.
Okay, thanks for trying.
Yeah, yeah.
Watts of electrical power are used by a 12-volt light bulb that draws 0.2 amperes. So how many watts? So watts is volts times current, right? Yeah. So 2 times 12 is 24.
2.4.
But then you got to move that decimal over. So I'm guessing A
Oh,
myself. What do you think?
um,
A. Yeah.
0.2. Yeah.
Yeah. 0.2 times 12 would be 2.4.
Yeah.
They say capiche, capiche. Oops. All right. So that's the kind of math they want you to do on this test. How many watts are consumed when a current of 7 milliamperes flows through a 1250 ohm resistor? So it didn't say, there's no K's there. Okay, so 7 milliamps would be 0.007 times 1250. Uh, I can't do that. 7 times 12 is 62. No,
So that'll give you 8.75 volts times 7 milliamps, right?
that's what I don't know. I need my calculator here. I can't do that. But 7 point 007.
61 milliwatts.
I think that's right. Squared. Hmm. Oh, fine. 1250.
So if you take 7 milliamps times 1250 ohms, that'll give you the voltage. And then times 7 milliamps, and that'll give you the,
Which is 61 milliwatts,
yeah.
right? Yeah. Yeah, I just pounded it out here on the calculator. Guess we could do the on-screen calculator. Um, but yeah, that's the kind of thing. So 0.007 squared times 1250. And that's what you want to, because me doing it on my calculator here don't really help you guys much, does it? Um, but there it is, A, milliwatts. I mean, it kind of makes sense because it's only milliamps here. So um, some folks will take like this 7 milliamps and take the other number as 1.25 kiloohms, and then the kilos and the millis cancel out when you multiply them. Anyways, I like using real numbers, low 0.007 squared times 1250. We'll get your 61 there. What percentage of power loss is equivalent to 1 dB? Now, this was in there, wasn't it? Was in that write-up we just did. But I found this one very hard. So the trick there is loss. So instead of putting in 1 dB, you put in a minus 1 dB because it's a loss. So what percentage of power loss is equivalent to 1 dB? So minus 1. You know, oops, darn it. I just worked through this, but and that was the last one up here. Would it be better if we went up there? Because it's -1, but this is where I miss this chalkboard. Because I hate to just point to all this stuff. So -1 divided by 10, and you got, let me try to back up here, okay? I'd rather go to the example they had here in the book. Here you go. So they're saying it's a -1 dB, right? And they want to know this power ratio, okay? So what you have to do is take 1 dB here where it says dB, you put a 1 there, a -1 there, and then you divide both sides by 10. So you get a -1 over 10, which is a -0.1. So then you take the inverse log of a -0.1, and that's your power ratio. This little calculator thing. And then, of course, you have to multiply it by the reference. And that gives you you want to go through it with a real calculator?
Yeah, I gotta find my slide rule.
Let me see if I can find my calculator here. There it is. There we go. So a -0.1, and then you divide it by 10 because why do you do that? Well, you do it. Divide it by 10, and that'll give you a -0.01. Then you take the inverse log of that, which in this case you have to multiply 10 to that power. And I got the wrong number, didn't I? 97. And then subtract that from 100. And then, no, I didn't do that right. We better start over. Okay. According to the manual, you take a -1 divided by 10. That'll give you a -0.1. So that is the ratio. Then 10 to the -0.1.
I think you got to hit the function key.
That's better. See, now we got 0.79, which is the right answer. If you change the sign and add 1, it gives you the 20% there that we're looking for. 20.56, which is C. So should we do that again? I found this one's kind of, as you can see, I confused it the first time. But and this is really really on the test. So a loss of 1 dB. So 1 inverse. So it's a -1. That's what really fooled me when I did this the first time. I just took 1 dB and divided by 10, and it's wrong. You got to have a -1 divided by 10, which is -0.1. Then you take the inverse log of that, which is the same as 10 to the -0.1, and that's your 79. So that's the amount of power that goes through the 79. Well, it's actually times 100 to get percentage. So it's 79% of your power is getting through, but they want to know what's the loss. So now you got to subtract it from 100. And I did that wrong. Thank you. 0.79 inverse plus 100. Oops. 100. That's still wrong. Well, I am just messing this calculator up. 0.79 inverse plus 100. Boy,
No, you want a -1.
-1.
Yeah,
Oh,
0.79 -1.
okay. We'll try that one. 0.79 inverse plus 1. Yeah, okay. I was getting my, and then you take it times 100 to get the answer of 21%, or 20.6, actually, which is the closest one there. And the answer is C. Let me go back to the other one. Nope. That better? No, it's not picking it up. You don't see that, do you? Um, um, there. Oh,
I think that answer was 20.57% loss. So that 20.6 in the questions would be right.
lost. I lost the page. There you go. 20.6, is that what you said?
Should be number C.
Yes, sir. C.
Yeah, yeah. Okay, we agree. Yeah, that's that I thought was a trick question because um it's a loss and you go through your calculation and you're getting the power through, not the loss. So then you have to turn it around to the loss and turn it into a percentage. Do I need to go through that again or do we move on? I just got lost in that calculator move I did here. If you want, we can try it with the calculator again. If you want to see it. Or am I making it worse? We'll do it again then. No answer. There's the 21. Okay. Where to go? Where? So, yeah, so there you go. It's 1 dB loss. So that's a -1. But then you have to divide it by 10. So let's start there. 1. Where's the -1? There it is. Okay, so there's a -1. And then you divide by 10 because it's power, right? So the equation's 10 times the log of the ratio. So we'll multiply it or divide by 10. So we divide by 10 and you get the wrong number. Point 0.1 negative divided by 10 equals
0.21, no.
I'm going to try again. Sorry, guys. As soon as I find that one. Okay. 0.1 negative divided by 10 equals 0.01. That's better. And then you do the inverse log of that, which is 10 to the x. And there's your 97, which is the wrong number again, isn't it? Boy, am I struggling with this one. 1 dB of loss on inverse divided by 10 is 0.1. The inverse log is, there you go, 0.79. I don't know how I keep getting that 99, but once you got the 79, then that's the power through. So the power loss is that much from 1 or plus 1. And there's your answer, the 20%. Now you can multiply it by 100, but to get that out to percent. But there's your 20.56%, which rounds off to 20.6. Or you can memorize the answer C. But that's the way to do it if you're going to do the math. There it is. 20.6 C. Okay. Now for some education here. Power equation is very clear for DC. P equals E squared over R. However, what is the value of E for AC power? Not peak, not average, it's RMS. RMS. If RMS voltage is used in the equation shown for calculating power, the result for the AC signal is the same as an unvarying DC signal. The RMS for a sine wave is 0.707 times the sine wave's peak voltage. Next slide. This is pretty good. I mean, it has it all in one spot here. You got the 0.707, which is your RMS. You got your average power, which is 0.63. I'm not sure what that's used for, but it comes into certain things, especially meters, I think. And the peak to peak. But what's really you got to watch is this peak envelope power. I think they show that pretty well on the next slide. RMS is 0.707 times the peak. So a lot of times with a scope, you measure peak to peak because it's just easier to do. So you have to divide that by 2 to get to the peak. Backing up. So there's peak to peak over here. It explains it. It's from this peak to this peak. So, but the 0.707 is just a half of a wave. So it's I peak or E peak is what they're calling it, not peak to peak. Next slide. Oh, I went the wrong way. But no. Okay. So there you go. All in this very top equation, VRMS 0.707 times the peak, or V over 2, which is the peak to peak, times 0.707. Or if you want to be fancy, you can take the RMS times 1.414 to get the peak if you know the RMS. Now, I only like to remember one number, so I just remember the 0.707, and In this case, I just divide the RMS by 0.707. But you can remember your 1.414 and your 0.707 if you must. And then, of course, with peak to peak, you got to take 2 times it because the peak is just half of peak to peak. It's really all in the fine print, just carefully read the questions. It's particularly important to know the relationship between RMS peak voltages to choose components that have sufficient voltage ratings. And that what they're getting at here is the capacitors, in particular, the electrolytic and the other ones are very sensitive to overvoltage. So you got to watch that peak power because the peak power is what the capacitor is rated for. And, very rarely do you actually go to the peak. If it says it's a peak power of 100 volts, you don't put 100 volts in it. You keep a little margin there. You'll be blowing holes in it.
And do they just get that 0.707 because that's the sine of 45?
Um,
I'm guessing.
yeah, it comes out of the geometry. I don't know exactly. I think it has more to do with the
Well, the sine of 45 is 0.707. So
right. Yeah,
it's gotta be just the trig.
but like they said, it's
But why 45
it's the
degrees?
root mean square, so they're squaring as you integrate along that curve. They're squaring it and then find the root of that. So they're it's yeah. It's the power. It's not, as they say here, it's not the average. It's the actual power, which I guess has to do with the shape of the sine wave, wouldn't it?
Well, the sine of 45 degrees is 0.707.
But what's 45 have to do with it?
Well, that's the if you look at the it's the 45 is where it's at on the x-axis.
That's where it crosses, right?
Right.
Yeah.
So I don't know why they don't just say the sine of 45, but why 45?
So the manual, which I don't have here, they try to explain that a little better because they're squaring it. It's well, I'll look that up at break, okay? Sine wave with the peak voltage of 17 volts has what RMS value? And that's a pretty straightforward question, eh? Just 17 times 0.707, which would give you the 12 volts as the RMS value. Which is, that's really, if you have an AC voltmeter, that's what it's doing for you. It's doing the 0.707 times the peak. I mean, that's when we call it a 12 volt signal, we don't mean 12 volts peak to peak. Waveform formulas, yes. Well, we've been through these, haven't we? The relationship between RMS and peak voltages to choose the components of, yeah, we've been through this. Okay. Sine wave, we did this one. The sine wave with a peak of 100 volts has what RMS value? So a peak to peak voltage of 100 volts. So you have to divide it by 2 because it says peak to peak, and it's 0.707 times the peak to get to the RMS value. So as you can see, 100 divided by 2 times 0.707 is 35 volts. Is the RMS value of 100 volt peak to peak. Yeah. 100 volt peak to peak. So this is one that we should all know, huh? Since we all use 110 volts. A sine wave with an RMS voltage of 120 volts has what peak to peak voltage value? Well, there you can do the 1.414 times 120 and then double it to get to the peak to peak to peak, because they want to know the peak to peak, which is 1.414 times 120, and then you double it. And somewhere I've worked where they had that. We used to use that number. 120. The peak is close to 200 volts. Here we go with peak envelope power. Now this is the one I thought was, you got to pay attention, is the peak envelope power is the average power. So they're calling it a peak envelope power, but it's the average power of one complete RF cycle at the peak of the signal's envelope. A convenient way of measuring the max power of an amplitude modulated signal. Oh, that's where it came into the system there as an amplitude modulated signal, which actually sideband is a kind of amplitude modulated signal for sure. However, the definition is confusing, just as I said. See the definition for the AR manual, blah, blah. So we'll take a better look at that as soon as I can make my thing behave here. Clarification, let's hope so. Peak envelope power is the average power of one complete cycle at the peak of the signal's envelope. PEP is used because it is a convenient way to measure or specify the maximum power. We said that, didn't we? But this is what I wanted to show you, is this little gem here, which I thought kind of explained it a little better. So the peak envelope power, so this sine wave you see here, what they're really representing is an amplitude modulated signal. The up and, the high frequency is the sine wave there, and then the amplitude of it's going up and down. So they want you to pick the maximum of that envelope there where it says PEP, divide it by 2, and then multiply it by the to calculate the average AC power, you need to know the load impedance, the RMS voltage, measure that voltage, and at the very peak of the modulated signal's envelope. This is the peak envelope as shown in this figure. I thought they did a better figure here. Oh. Once the RF cycle is identified, we calculate the average power over its complete duration. That's the red area in this figure. There, that's the one. Although the words kind of confuse me. But as you can see, the arrows are pointing to the very peak of the power of the modulated signal. And that is your peak envelope power. Then you have to calculate the RMS of that. Note that we calculate the power in both the positive voltage half cycle and the negative voltage half cycle. They don't cancel out because it's showing the PEV is squared, making both of them positive. The beauty of squaring. Start by measuring the amplitude of the peak, usually in volts. This is the PEV in the figure on the previous slide. Then apply the following. Next slide. Calculations. So there you go. PEP divided by 2 times 0.707 squared over R. And there you go. PEV times 0.707, or VRMS, the voltage of the RMS, voltage converted to RMS squared divided by R. And they're probably going to do it for us here. For example, the peak envelope If the peak envelope is 50 volts across the 50-ohm load, the PEP power is 50 times 707 squared divided by 50, which is 25 watts. Let me go through all that. As you can see, the 0.707 times 50 is 35.35. Square that, you get 1249, and divided by 50, you get 25 watts. So, or you're going to have to do that with a multiple guess. If a 50 ohm load is dissipating 1300 watts PEP, the RMS voltage is, drum roll, what is it? I can't see. So, VRMS is PEP times R, the square root of PEP divided by R. Because, well, you square both sides. You get VRMS squared over R. There you go. So the square root of 1200 times 50 is 2.45 volts. If an oscilloscope measures 200 volts PEP across the 50 ohm load, what would the PEP power be? And see, they use the word oscilloscope, and that's where you use this peak to peak, because it's just the easiest thing to measure on an oscilloscope, because you can actually put a marker at the top and the bottom of the sine wave. See if I can get this to work. There we go. So 200 volts peak to peak times 0.707 divided by 2. You square it. You divide it by, well, you square it, and they get this 499. You divide that by 50, and you get 100 watts, roughly. For the same device at 500 volt PEP, oh, this was 200 volts, so we want to go up to 500 volt. What would it be? And the answer is, well, 625. Guess it's not an even multiple, eh? Well, anyways, there you go. 0.707 times 500 divided by 2. Square that, and then divide that by 50 to get your 625. Well, it must be time for some questions, eh? Here's the summary. PEP equals the average power if an amplitude modulated signal is not modulated. Oh. Okay, well, an example of this is when the modulation is removed from an AM signal, leaving only a steady carrier, or when the CW transmitter is keyed. An FM signal is a constant power signal, so PEP is always equal to the average power for FM signals. In other words, if an average reading watt meter connected to your transmitter reads 1260 watts when you close the CW key, your PEP will be 1060. What by this, to tell you the truth. Oh, that must be the end of this session, eh? It is. Break time, I guess. I didn't think that last one was very clear myself, but I guess we'll live with it. Oops. Stop screen sharing.
Actually, since we're here, it's 8 o'clock, so why don't we take a 10-minute break and come back?
I'll try to deconfuse myself.
I am going to talk about basic components, section 4.3, and don't worry too much if you didn't study it right now, because we will get back to some more of this, and there will be a review session in 2 weeks. So The next few slides are going to be sections of this diagram, which is on page 4-9 of your manual. These are schematic symbols for common components. And so we're going to get into what are the bits and bobs inside your radio here, and what do they do? So so I'm going to talk about basic components, and let me get the slideshow going here. Okay, and let me share this. Okay, can people see a slide that says section 4.3 basic components? That's
Yeah.
what's on the screen?
Yes.
Okay, so here we go. So I'm going to talk first about passive components, and those are components that do not amplify anything, but instead they are resistors, capacitors, and inductors. So here. So the three most basic components are resistors that resist the flow of electricity or convert it to heat, actually, and the values are measured in ohms. Capacitors are designated by C, and they store electric energy, and they're measured in farads, but that's a little bit misleading because a farad is a very big unit. So what you commonly see are microfarads and even smaller units than that for practical components. Inductors are designated L, and they store magnetic energy, and they're measured in henries. And again, henries, 1 Henry is a fairly large unit of inductance. So you're more likely to see practical components with values of millihenries and microhenries. And then practical components include ratings such as the nominal voltage, the tolerance, the temperature coefficient. In other words, how much does the value of a component change as it warms up or gets cooler, and the power rating for the component, so you don't blow it up. So, for instance, if you have if you look on the printed circuit board of a radio, most of the resistors are fairly small, um, about half as thick or even thinner than a pencil, but they're designed to dissipate at most 1/4 watt or 1/2 watt. Some of them are an eighth or a tenth of a watt dissipation rating. So you would use them there, but if you were to put if you were to plug in a light bulb to the wall socket and then put a resistor in series with that, that resistor would dissipate several watts. So you'd want a physically much larger resistor, and you'd need something to handle the heat also. Anyway, let me see here. So these are the symbols for resistors, and most resistors are either fixed or variable. And on the lower left, a potentiometer is something to use, for instance, for a volume control, where it's a variable resistor where there's a wiper arm. There's a wiper arm that moves across a that moves across a resistive fixed piece. And so by turning the knob or moving that wiper arm, you could change uh, the resistance between one end of the fixed part and the wiper arm. Occasionally, you will see things called photoresistors, which change the resistance depending on how much light falls on them. Those are not used very much anymore. Um, you might find them in things like the if you have a garage door opener, you'll notice that there are little boxes on opposite sides, and one side sends a beam of light, and the other side senses if it's been interrupted. Uh, so that way, if you walk into the garage, the beam of light will be broken, and it will turn on the garage lights, or if you stick your foot in there, or if there's a piece of lumber or something like that that is next to the door and breaks that beam of light, then you won't be able to close the garage door on it. Anyway, other than that, you don't see photoresistors very much. And there's also something in the lower right called a thermistor. And a thermistor is designed to deliberately change value by quite a lot depending on the temperature. And you can use those to actually measure temperatures. All right, so let's go on. A capacitor, the symbol for a capacitor is basically, two plates that are separated by a gap, and that's the way they work. Charge is stored on plates on one side of the capacitor, and pushed away from. So one is charged positively and the other is charged negatively. And you usually see fixed capacitors or variable capacitors. Capacitors with large values are electrolytic capacitors, and those are in the tens or hundreds of microfarads. You see those in power supplies, and they are polarized because the two plates are actually, the plates will be two sheets of metal that are sort of wrapped into a roll, like I'm trying to think of it, like a Swiss roll, I think, is the pastry. But in an electrolytic capacitor, there is a chemical film that's very thin, which allows you to pack a lot of capacitance and hold a lot of charge in a small volume. But that film only forms when you apply the positive voltage to the positive terminal. If you reverse it, you can blow up, you can get nice smoke to come out of the capacitor. And then there are variable capacitors, which are usually used for tuning. If you look in the inside of an old radio, that has a dial that turns when you turn the knob. If you look in the inside, you'll see a variable capacitor that there's a fixed section that has a whole bunch of plates that are half circle, and there's a moving part that fit in between. And as the plates move past each other, there is a larger or smaller area where the plates are in front of each other, and so you can vary the capacitance there because the capacitance is proportional to the area of the two plates that are next to each other. An inductor is a coil. So when you pass a current through a coil, you get a magnetic field. And these different symbols show different kinds of inductors. An air core coil is just wire wound in a spiral, or rather, yeah, it's wound in a coil like the ramp in a the circular ramp in a parking garage, for instance. Um, if there is an iron or ferrite core, iron or iron compound core inside the inductor, then you'll see those two parallel lines next to the symbol for the coil. You notice that the symbol, the basic symbol, looks like the turns of a coil.
And releases energy much faster. This is very useful, and that's why you'll find capacitors used in almost every circuit board. So
Somebody needs to mute.
I want you to first think of a water pipe through it. So we let it flow until we shut the valve. Then,
Who's talking about pasta?
if after the valve we first let the water flow into a tank, then the tank will.
There we go. John, I think that might have been you. Anyway, there are also variable coils, and the ways those work are either you move the core in and out of a coil, which changes its inductance, or you move a variable arm along the coil that a certain number of turns of the coil are in use. And that way you can get, well, it's a coarser adjustment, but you can get different values of inductance that way. And then on the lower left, there's a thing called a ferrite bead. Some inductors are supposed to be very good about magnetic fields, the magnetic fields that they produce. But on the other hand, what you want sometimes is not to pass radio frequency currents from one part of a circuit to another, and that's where ferrite beads come in. You can make coils that are deliberately very lossy. In other words, for radio frequencies, the radio frequency energy is dissipated as heat, but DC currents can pass through, direct current can pass through. So those are ferrite beads, and you will see those to control radio frequency traveling around a printed circuit board, or to make sure that RF does not escape from a piece of equipment out onto the wires that connect to it. So, okay, and then this is probably one of two slides where you will see a tube. Tubes have tubes are glass or metal envelopes that have vacuum inside, and the types of tubes depend on the number of grids in them. But if you look at the triode here, you'll see at the bottom there's a filament. This thing at the very bottom that's sort of triangular shaped, and that heats up, and the next element above it there is a cathode, and so the heat from the filament, literally boils electrons off of the cathode, and they travel to the anode, which is the top element there. And then in between, there are one or more grids, which are what it looks like. And the voltage on the grid makes more or fewer electrons reach the anode, and so you can control the amount of current flowing from the cathode to the anode by a higher or lower voltage on the grid. And then one special kind of tube is that cathode ray tube, or CRT, which is an old-fashioned TV tube. And the only place you'll see CRT these days is in an old TV or an older oscilloscope. Cathode ray displays have pretty much been replaced by liquid crystal displays, which are which use electric fields to change the light passing properties of chemicals between. Chances are you have one tube in your house, and that is the tube in your microwave oven. But even those are being replaced by solid state transistors that generate microwaves at high power. So tubes are kind of on the way out. The transistor was invented, I think, in 1957, and by the 1960s, you started seeing transistors show up all over the place, particularly in those little portable radios. And probably by the 1990s, vacuum tubes were gone from all but a few very specialized applications, usually involving high power. So I might have another slide to show about tubes later on, but that's about all you need to know. So these are schematic symbols for wiring. And I'm not going to spend too much time on this, but the thing to know is that if you see, the convention is if you see two lines that cross, those are two wires that are not connected. But if you see a dot at the intersection of two lines, that means they are connected, like the middle one on top here. If you see a wire ending in a circle, that's a terminal or a connector. And then there are other things that designate things like shielded wire, where the outer part there is a shield that keeps stray signals from getting into the center conductor of the cable. And sometimes you'll see in the bottom center a bus designated as a line, or a line with a slash through it that says how many conductors there are, and you'll see individual signals broken out from the bus. And this is common for digital schematics of digital circuits. So let's look at resistors and resistance here. There are several common types, and the ones you'll see most common are in the upper left of the image there, carbon and metal film resistors. So a carbon composition resistor has graphite in it, sort of like pencil lead, and depending on the composition of the filler there, the resistance can be higher or lower. Metal film types have a tube of metal film between the ends, and that has a certain amount of resistance per square area. And so you get the resistance you want by changing the composition of the metal compound. And those are generally low power resistors that you see in electronic circuits that don't involve that involve power levels of under a watt. And then when you get up higher than that, you see you see larger components. Thick film resistors, continuing on the left, are when you can see one of them. You can see a sort of wavy line, and that's a trace of a resistive film that the current flows through, and by the composition and the length of that line, you can see. I'm sorry, you can change the resistance. Thin film resistors do that with even thinner resistive films that are deposited on non-conducting substrates. And most of the surface mount resistors you see, those little things, you see 1002 there on 4 of them. And are those joined? That doesn't make sense. But most surface mount resistors are thin film, and surface mount are the little rectangular things that you see when you open up a modern piece of electronics. Um, wire wound resistors, on the other hand, use resistive wire. They have tungsten or nichrome wire in them, and those are designed so that uh, they can dissipate a lot of power. But also because the resistive wire is wound in a coil, they also have inductance. So you don't use wire wound resistors in radio frequency circuits. There are special purpose resistors designed to dissipate a lot of power. For instance, for a dummy load, you might want a dummy load that's rated at 100 or 200 or even 1500 watts. And so you need resistors that are built to withstand a lot of heating. If you consider, for instance, a space heater will only dissipate a couple thousand watts, and that is enough to heat a room. So you really have to watch out for that. Okay, so anyway, where was I? All right, so and then on the right you see variable resistors, and a variable resistor is sometimes called a potentiometer because it is sometimes used to change to adjust the voltage that's applied to or electric potential that's applied to at some point in a circuit. So the values you can see on leaded resistors in the color code, and I'm not going to go into that, but there are a lot of hands who can recite the color code by heart and decode it very easily. Pardon me. The values can range from of an ohm up to tens of megohms, and usually what you'll see are values between a couple hundred ohms and maybe 10,000 ohms used in radio circuits. And then they also have tolerances. How accurate can you make the resistance? Surface mount components and some carbon film resistors have a tolerance of 1%. So if I say I have a 1,000 ohm resistor and the tolerance is 1%, it can be anywhere between 990 and 1,010 ohms. If I say it has a tolerance of 5%, then it can be anywhere between 950 and 1,050 ohms, and so forth. And the tolerance is sometimes very important to make a circuit work right, and sometimes is less important. What you'll find is that, again, surface mount components, because of the way they're manufactured, most of them come in 1% tolerance for resistors. But it's common to see tolerances, value tolerances anywhere between 1% and 10% of the nominal value. Oh, okay. There are different units of resistance, and I have a thing here. If people ask next week, I can go through a whole thing, but there are standard ways to refer to units in the metric system. And so if you just have the unit like ohms there, that means that you're stating the exact number of ohms. If you have kiloohms, those are thousands. So kilo is a prefix that means thousand. And for instance, you can see that in units like kilogram and kilometer or kilometer. Meg is a prefix that means million. And so besides megohms, you can see it in things like megabytes, for instance. So meg or mega means millions. And so to convert, if you want to convert from ohms, if you want to convert from ohms to kiloohms, you divide the value by 1,000, or to convert to megohms, you divide by 1,000,000. To convert kiloohms to ohms, you multiply by 1,000, or to megohms, you divide by 1,000. To convert megohms to ohms, you multiply by 1,000,000, and kiloohms, because that's in between. To get thousands from millions, you multiply by 1,000. And then for values that are smaller than one, there's another set of prefixes, milli, micro, and so forth. And we'll see that with capacitors. So the example here is 150 ohms is 0.15 kiloohms, or 0.00015 megohms. On the other hand, 150 kiloohms is 0.15 megohms, and 150 kiloohms is 150,000 ohms. So I hope that's clear, but you'll see these prefixes all the time, and understanding that kilo means 1,000 and mega means million will save you a lot of time. Oh, here we go. Okay, so 4.7 kiloohms is 4.7 times 1,000 ohms, or 4,700. And 4.7 kiloohms is 4.7 divided by 1,000 is 0.00047 megohms. And what you see typically is you'll see values between 1 and 1,000. And then the units will be ohms or kiloohms or megohms, depending on, I'm sorry, the way it's written is a number between 1 and 1,000, and then a unit of measurement that reflects the actual value. In other words, ohms or thousands of ohms or millions of ohms. And that's to make the designation of values easy to read. So, and you can see here, 2.2 megohms is 2.2 million ohms, or 2,200 kiloohms when you do the conversion in between. Inductors. You can see an inductor is a coil here, and you can see that on the left, that air core coil is just a piece of wire wound into a coil of loops, and so the inductance depends on the amount of wire and the spacing of the wire, but is not boosted by any core that's more magnetically conductive. A variable coil, you can see here that this arm at the top, if you see the arm just below the top, there's a contact that rides on a copper arm, and the contact will grip the wire on the coil, and as you turn the knob, the contact slides back and forth, so it includes more or fewer turns of the coil. And on the right you'll see a coil with a magnetic core. In this case, it is a ferrite core, and when a coil is wound on a circular form like that, it's called a toroid, or the core is called a toroid, and you'll also see the coil referred to as a toroid. So you can see there are these different kinds. Double lines indicate a solid magnetic core, and iron and different iron compounds can boost the inductance of the same number of turns on a coil, depending on something called their permeability. Variable inductors often have solid cores, and in that case, very often what you'll see, besides this thing in the picture, where a contact slides back and forth to contact different number of turns, you'll see that the core can be slid or screwed partly in or partly farther out of a coil, and it changes the inductance that way. And miniature inductors can look like resistors, either the former resistor. Well, let's go back to the resistors here for a second. So this thing that says carbon and metal film for resistors, inductors can take that shape too. And then inductors can be these little squares where it says thin film, or little rectangles when they're surface mount components. And you have to actually know what they are by the markings, or know what they are before you try to use them, so you don't use the wrong kind of component that looks like a different kind of component. So anyway, okay, so let's go back through this. So the design of inductors is proportional to the square, the inductance, or the ability to generate a magnetic field or store magnetic energy, is directly proportional to the number of turns, and the square of the number of turns and the square of the area enclosed by each turn. So making an inductor longer, if you pull the turns apart, you reduce the inductance. If you squeeze the turns together, you increase the inductance. And as a matter of fact, that's a way of adjusting coils that you'll find that radio hams do a lot. Increasing what's called the permeability of the medium inside a coil is how you can increase the ability to store more magnetic in the same amount of volume. And so air, for instance, has a very low permeability, and iron has a relatively high permeability, and ferrites are somewhere in between. So you can control for a given size of coil, you can control the inductance by the material in the core, and also by the number of turns and how they're spaced in the coil. So type of coil and the type of winding affect the inductance, and they vary according to the way the inductor is used. Variable inductors are often used in low power receiving and transmitting applications. So as I was saying for the previous slide, you can move a core in and out of an inductor. You can adjust it to move it partway in or out. Or for high power inductors, for instance, in antenna tuners, you'll see these sliding contacts, so that you basically increase the number of turns in a coil that are active, or reduce the number of turns that are active. And so let's get into prefixes again, and these are standard prefixes. For instance, you see millihenries here at the bottom of the slide, and at the bottom of the first column. And you're probably familiar with things like millimeters and milligrams for distance and weight. So milli means 1/1000th. Micro means 1/1,000,000th. Millihenries and microhenries are very common. Millihenry coils tend to be in power supplies where the frequencies that you want to deal with are low. Microhenries tend to be values for radio frequencies. And then nano is a prefix that means 1/100000th. So you will see some coils, some inductors that are specified in nanohenries, and those tend to be for very high frequencies, or where extremely small values are needed in circuits. So the conversions here are, again, conversions between thousandths, millions, and billions. Don, did you have a question? Okay. And I'm not going to go through all of this, but understanding what the prefixes mean, it should be very, very easy to convert between different units here. So, for instance, 330 nanohenries, which is NH, are 330 divided by 1,000, or 0.33 microhenries. And this sort of reverse U here is the Greek letter mu, but you'll just hear people say UH or microhenries. And then uh, okay, and then 330 nanohenries are 330 millionths of a millihenry. Now you'll occasionally see inductors that are as large as 1 Henry, but those are in very high power applications, and generally to filter things like AC current coming from the wall socket. 6.8 microhenries is 6,800 nanohenries and 0.0068 millihenries. And again, from micro to nano, you multiply by 1,000, and from micro to milli, you divide by 1,000. Millis to nano are multiplying by 1,000,000, and millis to micros, you multiply by 1,000. So you could see all of this stuff in the book, but you should brush up on the questions, because you'll see things like this. And this is the reason these conversions are important is in some equations, what you want is to have everything in the same units or the same scale of units. So sometimes you need to convert between one scale of unit and another. So inductor coupling, if you put two inductors close together, the same magnetic field circulates through both of them. And sometimes, and if the axes are aligned, so if you think about the magnetic field from a straight line from a straight coil, the magnetic field is the most the intensity of the magnetic field is the strongest inside the coil, but the magnetic field extends beyond the coil, and so if you put another one right next to it, the magnetic field will affect the second coil. So, and well, here's the illustration. Sure. So what you see is when you open or close that switch, current will flow or stop flowing in the coil on the left, and that will induce a voltage in the second coil. And sometimes you want that and sometimes you don't. What you'll see very often is if you have coils in a filter, for instance, that aren't supposed to interact with each other, they'll be at right angles with each other, or coils will be shielded in metal cans so they don't react with each other. But sometimes you want this. So magnetic field from one inductor can energy with another inductor. And that's called coupling. And the ability to share or transfer the magnetic energy is called mutual inductance. So if you wind the coil in so it fits on a circular form on a toroid, then what happens is the magnetic field that's centered inside the coil will basically stay in, most of it will stay inside the core, and very little of it will get out to the outside world. So if you put another coil next to this one, very little magnetic energy will be transferred to the second coil. And so this is very useful in RF circuits. So for instance, if you open up a transmitter and you look at the filter between the power amplifier and the antenna, which is designed to prevent harmonic frequencies from getting out, you'll see that there are usually a bunch of these coils, several for each band, several for each handband. And if they're wound on toroids, they can be placed pretty close to each other without any appreciable coupling between them. So the composition of the cores makes it possible to obtain a wide range of inductances in the same volume, basically. And toroids because they are circles or donuts are relatively small compared to cores to coils wound on a straight core or air core coils. So the composition of the coil varies, and we won't get into that here, but you can find a wide variety of inductances. You could make a wide variety of inductors from the same winding on different core materials. Also, for what it's worth, ferrite compounds are more effective at certain ranges of frequencies. So you'll see people talk about the mix of the core, the ferrite mix of the core. And some of them are better suited for the lower hand bands, some of them for the upper HF bands. Some of them are better suited for a relatively narrow range of frequencies, and some for broader ranges. And that's a bit of a black art. So, but you'll see people choose different kinds of cores depending on the frequency and the application. The mix of the core. So that's what I was just talking about. So let's do some practice questions here. We're going to look at schematic symbols here. And the first is, which symbol here reflects a field effect transistor? Symbol number 2, which is in the circle on the right. Symbol number 5, which is the thing with the zigzag top in the top middle. Symbol number 1, which is the circle with the arrow and pointing toward the vertical bar. Or symbol 4, which is the thing on the left that looks like a diode plus a capacitor. Guesses, anyone?
It's either 1 or 2.
I'll say 1.
Okay, so the answer is Charlie, symbol number 1. I'm sorry, symbol number 1, that's right. So a field effect transistor, oh boy, we're going to get into transistors in a few minutes here. But a field effect transistor and a bipolar junction transistor, which is component number 2, work on different principles, and their schematic symbols are somewhat different. And different kinds of diodes which conduct electricity in one direction, which conduct current in one direction only, are symbols 3, 4, and 5, and they have different properties, and so they have different schematic symbols. And I'll get into that also. Which symbol represents a Zener diode? Symbol 4 on the left, symbol 1, which you already know is a field effect transistor. Symbol 11, which is, where's 11 here? No, I'm not seeing 11. Where's 11?
Upper left.
Oh, okay. Okay, yeah. Upper left, or symbol 5, which is in the top center.
It's either 4 or 5.
Yeah, okay. So the answer is D, symbol 5. Sorry, I didn't warn you about these things.
Zener diode. Okay.
Which symbol in figure G7.1 represents an NPN junction transistor? Symbol 1, 2, 7, or 11? And this should be easy. I think I gave you the answer already.
It's either 1 or 2.
You know, it's not one.
It's got to be 2.
Got to be 2. So the answer is bravo, symbol 2. Yep.
Sister.
Which symbol represents a solid core transformer? Now, a transformer is 2 coils that are deliberately coupled, and we'll talk about those later too. Symbol 4, 7, 6, or 1?
6.
Yep, symbol 6, or Charlie. Which symbol represents a tapped inductor? In other words, an inductor that where one of the leads is partway up the inductor. Is it symbol 7, 11, 6, or 1?
7.
Yeah, it's 7.
Where is 7?
On the
Oh,
lower left there, the lower left corner.
okay.
Now, yeah, so it's A, symbol 7. Now, the reason you want a tapped inductor is in some circuits, particularly filters, you'll want to connect another component so that you want to connect another component so that the current flowing
You
through.
don't have to use two inductors.
Yeah, right. So you have one current that flows from the top to the bottom of number 7 there, and you have another current that flows from the tap where the wire comes in near the bottom to the bottom through fewer turns. And the idea is that makes that tap coil look like a transformer. So instead of 2 windings, you have 1. And I'm sort of hand waving a little bit here, but there are circumstances where that's perfectly fine if you want to use the transformer property of a coil by tapping in at a certain point.
And they call that an auto transformer.
Yeah, an auto transformer, that's right. The auto because the winding, instead of 2 windings, the 1 winding acts on itself. What determines the performance of a core at different frequencies? Its conductivity, its thickness, the composition or mix of materials used in the ferrite core, or the ratio of outer diameter to inner diameter?
Composition, probably.
Yep, it's composition, Charlie. What is an advantage of using a ferrite core toroidal inductor? A, large values of inductance may be obtained. B, the magnetic properties of the core may be optimized for a specific range of frequencies. C, most of the magnetic field is contained in the core. Or D, all of the above.
It's either C or D.
C.
Well, we have a couple of C guesses, but the answer is actually D. It's all of those things. Depending, and because the toroid because the toroid core has is made of a material that has a higher magnetic permeability than air, you get a larger value of inductance for the same number of turns in the coil that's wound around it. And then answer B is a little bit weasel worded, but the idea is that the mixes of the ferrite material in a toroid core work better at some frequencies than at others. Their properties are more desirable at some frequencies than at others, and it depends on the composition of the core material, and all of that. That's something you can get into arguments with Hans about. What's the best toroid to use for doing ABC? Capacitors and capacitance. Okay, so now we're going to get into this. And what you can see on the right hand are some different types of capacitors. They have 2 conducting surfaces that are almost always metal, They're called electrodes that are separated by a thing called a dielectric, or you'll hear dielectric also. But um, a dielectric has a property. A dielectric is a thing um, that controls how much of an electric field how much of an electric field you can put between two electrodes that are a certain distance apart. Um, Capacitance is the ability to store charge or electric energy measured in farads. But as I was saying before, you'll typically see microfarads at almost a maximum of microfarads or nanofarads or picofarads. Capacitors block a DC current flow. Now, inductors, on the other hand, uh, will to a certain extent block AC current flow. So the higher the frequency, the more an inductor will block alternate currents, and the higher the frequency, the less a capacitor will block AC currents. The simplest capacitor is a pair of metal plates separated by an air gap. And so if you put two metal plates close to each other, like a quarter of an inch apart or something, you will get a capacitance that you can measure. And as a matter of fact, that's something, that's a science experiment kind of capacitor. The components that you see are more miniaturized, though, and they're made by multiple layers of electrodes that are connected to alternate terminals. So you'll have positive, negative, positive, negative, positive, negative. Um, and they and the idea is you get more capacitance by placing the electrodes as close together as possible, but not so close together that they arc over or touch each other and start conducting. So the dielectric material makes a difference, and there are several chemicals and solid compounds that have a higher dielectric coefficient, is what it's called, than air, and so you get capacitance is proportional for the same area and spacing of electrodes. You get a capacitance that's proportional to the dielectric constant of the material between them. So electrolytic capacitors and tantalum capacitors are polarized, meaning that the DC voltage can only be applied in one direction, because otherwise current can make a permanent chemical reaction or permanently damage or short together the electrodes of a capacitor inside. So electrolytic capacitors are typically used for applications where you want to filter a DC voltage and get rid of any AC component that's on it. Or, basically that. Capacitors have voltage ratings, and if you exceed the voltage rating, the peak voltage rating of a capacitor, then the capacitor might arc over, or it might damage the dielectric material that's inside it, and that way you can destroy the capacitor. If a capacitor with an air dielectric arcs over, then you can sort of see the burn where the spark crossed over, and that can have some effect, but typically air dielectric capacitors, which are basically just metal plates, can stand a little bit of abuse, certainly more than the than the smaller ones with solid or liquid dielectric. And one thing you'll notice for what it's worth is if you see capacitors that are used in higher power applications, again, such as antenna tuners, you see that their plates are spaced fairly far apart, like a quarter of an inch apart, for instance, where if you see a tuning capacitor in an old radio, which just has a few volts across it, you'll see that the plates are spaced by only about their own thickness apart from each other. So let's see. Capacitor types. Ceramic capacitors are good for radio frequency filtering and bypassing at high frequency and basically filtering out radio frequencies. And they are low cost, but also they're they tend to have wider tolerances than some other types. Plastic film capacitors are generally used in low radio frequencies and for audio circuits. Silver mica capacitors are very good. They have low losses, which means that they act as pure capacitance, and there's something called equivalent series resistance, where the resistance of the wires and the metal in a capacitor will act like a hidden resistor in series with the capacitor itself. Silver mica capacitors are low loss. They are highly stable, meaning that they don't age very much. The value doesn't change very much with age or with temperature for that matter. So they're used in radio frequency circuits a lot. Electrolytic and tantalum capacitors, because they have chemical dielectric, are generally used at fairly low frequencies and in applications like power supply filtering. And air and vacuum dielectric capacitors are used in transmitting circuits where there's either high voltage or high power passing through them. And the reason for that is it's much easier to control arcing, or it's much easier to get higher voltage ratings if you have air between the plates of a capacitor, or even better, when you have a vacuum, which is non-conductive between plates of a capacitor. So what are they used for? They're used to block DC signals while passing AC signals, and that's called blocking. They're used to provide a low impedance path for AC signals around a higher impedance circuit. And bypassing also means sometimes you want to shunt radio frequency signals to ground so that they don't travel farther in a circuit. And so you see bypass capacitors, small values connected between, for instance, on a digital IC or a microprocessor, between the power wire and ground, so that any voltage spikes that are generated by the digital circuit get filtered out and don't travel to other places in the circuit. And then a filter capacitor is something that can store a fairly large amount of charge, meaning that it can respond to different current drains from the capacitor. So you'll see that in filter circuits, and I'll show you what a filter circuit looks like farther on in this chapter. In a power supply, that is. And then suppressor circuits. Sometimes you want to just absorb the energy of a voltage spike or a voltage transient, which contains very little power, but also has voltages that can damage other components. Now, this is not the same thing as a lightning arrestor, but you'll sometimes see capacitors used to absorb voltage spikes in a circuit. And then a tuning capacitor you can build circuits out of coils and capacitors, inductors and capacitors that are resonant. In other words, they respond best at one frequency. And by changing either the inductance or the capacitance in the circuit, um, you can tune that circuit to be resonant at different frequencies. And and the easiest way is usually a tuning capacitor because those are easier to build because basically you just put one set of metal plates on a metal shaft that you can rotate, and the shaft is insulated from the fixed part of the capacitor. Um, and as I say, look in an old radio sometime and you'll see these, or look in an antenna tuner sometime, and an antenna tuner with knobs on the front, and you'll see these.
I got a couple here, Wes.
Oh, okay. Let me stop sharing for a second.
Focus very well, though. Huh.
Well, all right. Let me stop sharing for just a second here. So, okay. Can everybody see what John is holding up?
See, this is an old-fashioned variable capacitor where these plates are on a shaft. Used to be the tuning dial would turn the shaft and change how much of the plates overlap here. The 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 plates, one's connected to one terminal, and then the other set of plates is connected to the other. And
Turn it over, John, so people can see the plates meshing together. No, turn it all the way over.
yeah, you can't see too much here.
Oh, well, okay. I was hoping.
Yeah, you can. I should set it up better with and then this is one of those variable inductors Wes was talking about.
Oh, yeah,
There's a
yeah.
little
Okay.
roller here. Um, yeah, I should rehearse this, eh? And as you turn
Yeah, but you can see a shaft, and what that shaft does is it turns the coil form, but because the connector grips the wire on the coil, it moves back and forth.
yeah, so you get another amount of a different, and these turns are kind of neat in that they're spaced differently at one end of the other, so that you have, um, more inductance per turn on one end and a lighter amount at the other for trimming it up. Um, I don't know. I bought this at a swap to make something and it never got made. But they're great for tuning antennas and stuff.
What I should mention is that when you get your general class license, it makes you more likely to become a pack rat.
Oh, well, some of that's personal. Some of that's
Okay,
personality. I've seen some guys that have really clean shacks. I'm not one of them.
No.
nor am I. Okay, I'm going to go back to the slideshow.
Yeah, I
So
just
you should see a slide now that says aluminum and tantalum electrolytic capacitors. Yes?
Yes.
Yeah.
Okay, there we go. So what they're designed to create a large capacitance in a small volume, which makes them very effective as filter capacitors. Um, so um, so the idea is you could store a large amount of energy, and if you think about AC voltage is varying all the time, but when you have a power supply that converts that to DC, then then at different points of the AC waveform, um, the voltage may be higher or lower than the DC output voltage. And what happens is when the input voltage is higher, the capacitor stores energy, and when the DC voltage input is lower, the capacitor discharges energy. And we'll go through the detail of that in a later section, but the idea is you want a large amount of capacitance so it can store a large amount of energy. And at the same time, you want all that energy storage in as small a volume as possible so that your radio doesn't grow too big. So
So
pendulum capacitors use a wet paste or a gel between pieces of aluminum foil, and they're usually rolled up into a cylinder so that you have both layers of metal spiraling out from center point. And the dielectric gel creates the insulation between the metal plates, and it also increases the amount of capacitance for the size of the plates, for the area of the plates. So
What happens when you destroy the capacitor by putting too much voltage on it? It punches through that paste to the other electrode and shorts out.
yep, you get a short circuit and you get very nice puffs of smoke.
And a big bang.
I think you may have done it more recently than I have, Colonel.
Don't the electrolytic ones blow up more?
Yes. And there's another thing you should know about electrolytics. If you talk to people who restore old radios, the first thing they'll do is replace all the electrolytic
Right,
capacitors. Because if an electrolytic capacitor isn't used for a long period of time, if it sits on the shelf for a few years, then the dielectric film won't form when you apply a voltage to it. But instead you get a short circuit. So old radio fans, when they restore these radios, they just replace all the capacitors with modern, with new units, which is kind of funny because of the advances in the technology. If you have a radio, for instance, from the 1950s, then the capacitors you get today are much smaller for the same value of capacitance and the same voltage rating. But I guess once the housing is on the radio, you can't tell the difference. Okay, some practice questions here. And what are we doing for time? Oh, geez. We are almost at 9:30, so I am going to go through these questions and then we'll stop at the end of this.
I'm gonna just
And then we'll pick up next week with active components. So anyway, which of the following is characteristic of an electrolytic capacitor? A tight tolerance, less leakage than any other type, meaning a leakage current for DC, high capacitance for a given volume, or it's an inexpensive radio frequency capacitor.
Charlie.
Yeah, it's Charlie, high capacitance for the same volume. Which of the following is characteristic of low voltage ceramic capacitors? A, tight tolerance, B, high stability, C, high capacitance for a given volume, or D, comparatively low cost? Yeah, it's D, delta. So electrolytic and ceramic capacitors generally do not have tight tolerances. You have to use capacitors like silver mica capacitors to get very tight tolerances like 5% or 1%. And also you have to get capacitors that are specially designed to get a low tolerance with temperature change. All right, so I'm going to stop here because it's well after 9. And so next week, and thank you everybody for sticking around also.
You're
Next
welcome.
week, I'm going to pick up again with transformers. So what happens when you couple coils on purpose? And then we'll get into active components. And so thank you everybody for sticking with me. Read further into chapter 4.
Okay.
And so I have I have some more to do on that, and John has some more to do on that over the next 2 weeks. And with any luck, 2 weeks from now, we will fit in a review session for all of this so we can make sure you have all the math down between decibels and logarithms and different units of component values and conversions and what else is coming up? Anyway, okay. So anyway, thank you everyone for coming tonight. I hope to see you all next week.